Welcome to another session of Circuits and Networks. In today's class 6 under GATE exam preparation, we are going to see a special theorem called Milliman's theorem. Yes, in GATE exam also, there are some problems which are frequently asked in past GATE exam regarding Milliman's theorem. So first, from the basics of Milliman's theorem, any voltage source connected in series with resistor and that series combination is connected in parallel as shown in this figure 1, that can be easily converted to a Milliman's equivalent network, which is shown in figure 2, by replacing the voltage with Vm and resistors with Rm. So you can go back to our previous classes under Milliman's theorem, how to derive this particular equivalent network, where Vm would be equivalent to V1 G1 plus V2 G2 so on divided by G1 plus G2 so on till Gn, where G is called as the conductance and Rm can be obtained by 1 by Gm. So these two derivations you can refer to our previous Milliman's theorem. Uh, Based upon these two equations, we need to solve, or we can say that we can apply direct shortcut to any gate-related problems related to Milliman's theorem, where Gm is regarded as G1 plus G2 plus G3 and so on. Therefore, Gm can be written as 1 by Rm, which is equivalent to 1 by R1 plus 1 by R2, so on till 1 by Rn. So from question number 1, which was asked in GATE 1998 for 2 marks. You can see AB is the equivalent network where we need to find out the parameters based upon the figure. It has to be reduced to an equivalent of a single voltage source in series with a single resistor with the following parameters. So the options were given like A, B, C and D, where you have option A as 5 volts source in series with 10 ohm resistor. Then you have 10 volt source in series with 2.4 ohm resistor. The third option is 15 volt source in series with 2.4 ohm resistor. And D option is 1 volt source in series with 10 ohm resistor. Okay. By applying Milliman's theorem across AB with the help of the formula of Vm given by this equation can be obtained as you can see V1 I am taking the value as 10 and G1 value is taken as 1 by 6 plus since we have only two sources, so we limit this formula to V1 G1 plus V2 G2 by G1 plus G2, and that is how the values from the given network is placed with the help of this formula. And solving this particular numerical, we are going to get the value of voltage as 7 volts. So clearly, option B is the right answer. Let us check whether we are going to get the value of resistor as 2.4 ohm or not. For that, we have the formula Rm is equal to 1 by Gm. So I'm applying the formula directly like this 1 by 6 plus 1 by 4, which is nothing but 2.4 ohm. Hence, option B is the right answer. So it is a basic level of Milliman's theorem. You can apply any other approach to get the same answer and comment in the chat box whether you got the same answer or not. In the next problem, which was asked in GATE 2019 for 2 marks, the current I flowing in the circuit shown below in amperes is. So it's a direct question. There is no multiple choice option. So we need to find out the value of current over here. So let us assume two terminals as A and B, where we are going to separate this 20 ohm apart, and the rest of the circuit will try to reduce to a Milliman's equivalent network. For that, when we apply Milliman's theorem to the left of AB, we get Vm whose value is equivalent to, see here you have 4 parallel combinations of 200 of voltage in series with resistors. So V1 will be 200, V2 will be 160, V3 would be minus 100 and V4 would be minus 80. And rest of the resistors taken the name of conductance is obtained as 1 by 50, 1 by 40, 1 by 25 and 1 by 20 respectively. So when I'm going to solve this equation, clearly 200 by 50 is nothing but equivalent to 4. 160 by 40 is also equivalent to 4. Minus 100 by 25 is once again is 4. And minus 80 by 20 is once again 4. So in fact, the numerator, the terms will get cancelled out and will be left over with Vm whose value equal to 0 volts. Let us also find out the value of Rm, which is 1 by Gm. That value would be equivalent to 1 divided by 1 by 50 plus 1 by 40 plus 1 by 25 plus 1 by 20. So this value here, it leads to 7.04 ohms. So when we reduce the given circuit to Milliman's equivalent circuit, that is Vm in series with Rm, and that combination is combined with the removed value of 20 ohms, which we have removed assumed over AB, that we are connecting over here. With that, I can easily calculate the value of current. Current I would be equivalent to 0 volts divided by the resistor which is in series combination. So 20 plus 7.04 would be 27.04. Anyhow, the answer would be equivalent to 0 amperes. So if at all you are good at networks, and if at all you are good at Milliman's theorem, by looking into the circuit itself, you can easily estimate the value of current, which is equivalent to 0. Why 0? You have two positive resistors values whose sum is 8 and two negative uh, negative value of the, sorry, not resistor, current value is equal to uh, minus 8. So 8 minus 8 would be equivalent to 0. So in fact, that would be the easy approach to get the solution for this kind of problem. So without wasting any time, the answer would be 0 amperes. So in a cross exam, for the circuit shown in figure like this, we were asked to calculate the Norton's equivalent current value in amperes and also the resistance in ohms. Again, you can solve with the help of Milliman's theorem, and you tell me whether you got the same answer or not. I'll employ Norton's method to get the solution, or you can apply even Thevenin's theorem also to find out the solution, and comment in the chat box whether you are going to get the same answers or not. For that, by applying Norton's theorem, we will try to find out the Norton's current, which is also known as short circuit current, and Norton's resistance, which is also called as Thevenin's resistance or equivalent resistance across AB. So that is what we are going to do with this problem. So to find out Norton's current, short the terminal AB as shown in the figure, and we can solve this either by mesh analysis or source transformation. So I'm shorting this terminal AB, and I'm taking three loop currents as I1, I2 and I3. So by mesh analysis, I can frame three loop currents, and if at all I'm able to solve these three loop currents, I will be getting the value of I1, I2 and I3. In fact, I2 value is nothing but 2 amperes. By looking into the problem, you can easily say the value of I2 is 2 amperes. Anyhow, let us apply KVL to this loop, which is carrying the current, loop current I1. So here you can see I'm applying mesh analysis, or in fact KVL, to the loop current I1. So minus 6 is the voltage source, plus 3 I1 is the drop over resistance 3 ohms, plus 3 I1 minus I3. Why I1 minus I3? Because here I1 and I3 are the loop currents, and their difference is treated as the branch current, which is flowing in this 3 ohms. Thereby, the drop over here would be equivalent to plus 3 of I1 minus I3, which is equivalent to 0. Reframing this equation as 1, let us go with the next loops. That is, we know that the I2 is equal to 2 amperes by looking into the dimensions of the current source, which is given in this fashion. I2 is nothing but directly equivalent to 2 amperes. And again, applying here loop 3, that is carrying current I3, the KVL. So that loop is treated to be the dominating loop. So 3 multiplied with the drop of current, multiplied with the current, not drop. The drop is nothing but 3 multiplied with I3 minus I1, plus again here you have another 3, that is I3 minus I2. All the current directions I have taken in clockwise direction. That is why I'm getting here as I3 minus I2. By looking into the loop 3, which is assumed to be here at the dominating loop, I have framed this equation. In fact, this equation can be reframed as equation 3. Now just we need to solve equation 1, 2 and 3, and we are going to get the value of I1 has 2 amperes and I3 also has 2 amperes. This 2 amperes of current is nothing but the Norton's current. That is the requirement of the problem. So the answer for this is 2 amperes. So half of the problem is solved. Again, in order to find out the equivalent resistance pertaining to the network theorems, whether it is Thevenin's theorem or Norton's theorem, we need to short circuit the voltage source and we need to open circuit the current source from the given network. So the given network is in this fashion, and current source is open circuited, voltage source is shorted. And I'm going to apply the equivalent resistance across AB, which is also known as Norton's equivalent or Thevenin's equivalent, which is nothing but this 3 and 3 looking from terminal AB on the opposite side, they are in parallel. That's why 3 into 3 divided by 3 plus 3. And that combination is again in series with 3. Why 3? Because you can see the circuit is framed in such a fashion. The 3 ohms is parallel to 2 amperes and 2 amperes is open circuited. Thereby 3 ohms comes into the series combination of this parallel combination of 3 and 3. So this will give you the value as 4.5 ohms. So answer for this problem which was asked for gate 1997 for 2 marks would be 4.5 ohms. You please solve this problem using source transformation and comment in the chat box whether you got the same Norton's current or not, or you employ Milliman's theorem in order to solve this problem, and tell me whether you got the same result, that is the short circuit current value as well as the Norton's resistance value, what we got here as 2 amperes and 4.5 ohms respectively. So that's how for today's class. Anyhow, GATE 2024 paper, that is last Saturday or Sunday, yeah, it was done first week of Feb. So anyhow, uh, now we have to concentrate on GATE 2025. So for that, we will analyze again GATE 2024, the problems related to ECE paper, that is electronics and communications paper, as well as triple paper, and we'll sort out some more problems related to our networks and circuits. I hope you like this class. Please share among your friends, subscribe to this channel, and please press the bell icon for the future notifications.